This is my cone, which I convert to more canonical form. It's a canonical form of the cone. But in this canonical form, I have to couple it with the extra assumption that z is positive, because otherwise it will take both the upper side and the lower side of my cone. That's a sphere. This is a canonical shape of a sphere. In fact, to do this question, you don't need to see the actual picture of the region. Everything can be done in terms of the inequalities, and I'll show you this. Look at this. So here's my spherical substitution from the slide before. Of this substitution, we know that rho, the radius, is never negative. We know that the theta angle, the, how do you call it, the longitude angle, right? The longitude angle normally is taken within these natural boundaries, negative pi pi. The latitude angle, well, it's a co-latitude angle, because the 0 corresponds to the north pole, whereas in the canonical latitude, the 0 negative pi on 2 corresponds to the north pole. That's arranged for the co-latitude angle, and that's the value for the Jacobian. These are the things we need to know to finish the question. So all I need to do now, I need to reinterpret these conditions of my region. I need to reinterpret these conditions in terms of my new variables, rho, phi, and theta. And that's the reinterpretation. Number 2, for the sphere, because we actually taking the region within the sphere, so actually within the ball, the condition, it just comes down to this. The radius doesn't exceed 2. The left-hand side, it comes from the natural assumption on the radius. You can even check this analytically. You can take the squares, sum of the squares of all of these right-hand sides with the basic trigonometric identity. You will see that this is just rho squared. Now, 1, the first condition, the cone condition, there are 2 here, z non-negative and this relation. Z non-negative, because rho is always non-negative, it just becomes the condition on cosine of phi. And within this region, cosine of phi non-negative in the first quadrant, when phi in this narrower region between 0 and pi on 2. That's my interpretation of this condition in the new variables. Within this full spread of phi of the co-latitude angle, only the first quadrant is the one which delivers positive value, because of cos here. Now the second condition in the 1, the cone condition, it's again, we just sub in right-hand sides in that condition. And that condition actually comes with this inequality, large, big, greater or equal, because we're taking the area above the cone. So z must be larger than right-hand side. So if I substitute that one, so here's this condition, you see I put the inequality here to reflect the fact that we take the area above the cone. This condition becomes, it's just direct substitution, or almost direct substitution. When you sum squares, when you take the sum of the squares of the right-hand sides of these two right-hand sides, because of the basic trigonometric identity, sine squared plus cos squared delivers 1, you end up with this, which you start solving. You can cancel out rho square, positive number, that doesn't affect the inequality. That's the cancellation. Well, you can cancel out and divide by sine square, which will deliver cotangent larger than 3, or I prefer to do it in terms of tangent. Tangent doesn't exceed 1 on 3. And that solves to this. Again, we disregard the negative values for the cotangent because we already know this narrower region for the phi angle. That's why we can be sure that the tangent is positive. That's why only this piece of the inequality matters. And this inequality actually narrows down this area even smaller, makes it even smaller, because tangent within this interval between 0 and pi and 2, tangent doesn't exceed 1 on root 3 here. And that's the finish of the reinterpretation. This original description of the region, in terms of the spherical coordinates, rho, theta, and phi, ends up to be these three independent inequalities. 1, 2, and we said nothing about theta, so we take this original unrestricted range for theta. 3 independent inequalities, double-sided inequalities, which means that the image of my ice cream cone, or pre-image of my ice cream ice cream cone, sorry, in the rho theta phi coordinates is the upright parallelepiped. Something for which Fubini works very easy. It's the upright parallelepiped with these boundaries in the rho axis. These are the boundaries, and the phi axis. These are the boundaries. Sorry, these are the boundaries in the phi axis. In the theta boundary, in the theta axis, these are the boundaries. So if I now move myself into this new space, into the rho theta phi space, my integral, my volume originally, of course, it's a triple integral of the unity across my omega area in the xyz plane. After substitution, here's my repetition via Fubini. Very easy repetition. It's because my area, my region in the rho, phi, and theta space, it's the upright parallelepiped. And I can say even more, because here again, if you look at the function, it's purely factorizable in the factors, in the pure rho factor, in the pure phi factor, in the pure theta factor. And you have upright parallelepiped. Such triple integral, or such repetition by Fubini, ends up to be a product of 3 individual one-dimensional integrations. Here they are. One pure rho integral, one pure theta integral, and one pure phi integral. Fubini for the upright rectangles or upright parallelepipeds, when function factorizes, I know you like it when I say parallelepiped. I can say it even more when you have the upright parallelepiped. And the function is purely factorizable into the pure rho, theta, and phi factors. That's the best way to do Fubini. Each of these individually we can evaluate. First one, well, that's the evaluation. First one is rho cubed by 3 with a double substitution like this. Second one is my typical statement I say. When you integrate a constant, you take the length of the underlying interval and multiply it by a constant. Length of the underlying interval 2 pi, constant is 1, that's why it's 2 pi. And for the sign, antiderivative negative cos. Everything else, I hope I did the arithmetic correctly. That's the value for the volume of my ice cream cone. So the question is, the solution itself, when you analyze this region, it doesn't really expect you to know to picture the image of it. Of course, it helps, but you can do analysis in a pure inequality way. Inequalities, inequalities, inequalities. Any questions?
This type of triple integral dx dy should be
Ah, thank you. This one I can fix quickly. Hopefully. Any other questions?